with the language of boundaries of three-dimensional solids at our disposal, we can now properly state the divergence theorem. But before we do so, let's review the concept of divergence and contextualize our conversation. So the main question that we want to address when discussing the divergence theorem is as follows. So let's say that we have a vector field F inside of a domain D. So here we have some sort of three-dimensional domain. Again, like the way to think about this picture is we're looking at some sort of closed surface, and then the domain includes that surface and everything inside of it. And then in our discussion, we're thinking about a vector field that lives inside of this domain. The question we want to ask is whether or not information inside of the domain here can help calculate the flux of this vector field over the domain, or over the boundary of this domain. In other words, can information inside of this domain help calculate the flux out of this domain? And the right tool for the job ends up being the divergence of a vector field. So let's remind ourselves what the divergence of a vector field is. The divergence of a vector field is defined as a symbolic dot product. So we write div f to refer to the divergence, and we can think of this as the dot product of the del operator with the vector field. And what this really means is that we take the partial derivatives of each coordinate of the vector field with respect to its corresponding variable, and then we add everything up. So we take the partial derivative of the first coordinate with respect to the first variable, plus the partial derivative of the second coordinate with respect to the second variable, so on and so forth. And it's important to remember that the divergence of a vector field is a scalar quantity, not a vector quantity. So if we take the curl of a three-dimensional vector field, we get a new three-dimensional vector field, but when we take the divergence, we get a scalar. And the use of the divergence of a vector field is that we can use the divergence to classify points as sources or sinks. So we say that a point in space is a source for a vector field if its divergence at that point is greater than 0. And what this means is that at that point, the net flow is out of that point. A sink means the opposite. A sink for a vector field is a point where its divergence is less than 0. And the way to interpret this is that here at this point, the net flow is into that point. So this idea naturally presents us with the so-called divergence theorem. So the idea is that the flux out of a domain, which is the surface integral of the vector field over the boundary of the domain, is supposed to measure the net flow out or into the vector field. Well, since the divergence is the scalar quantity that measures net flow out or in, what the divergence theorem suggests is that the triple integral over the three-dimensional domain of the divergence operator should be the same thing as the flux of the vector field over the boundary of the domain. So the divergence theorem states that the triple integral of the divergence is the flux out of the domain. And as usual, I like to track the units to make sense of the statement. So the divergence theorem states that the triple integral of the divergence over the domain is the same thing as the flux of the vector field over the boundary. Well, if we look at the units for divergence, remember that in this context, the vector field has units given by velocity, and then when we differentiate each coordinate, we're dividing by distance units. So the units on the divergence are 1 over time, and then dv carries the distance cubed unit, which is the volume unit. So when we multiply 1 over time by distance cubed, we get volume per unit time. On the other hand, if we look at our flux integral over here, we're looking at the force, which has units distance per unit time, and then d vector s carries the area unit, which is distance squared. When we multiply these two quantities together, we get distance cubed per unit time, which is volume per unit time, which is exactly how we define flux.